Oh, now you can see, right? So he has put it, okay. This paper reviews the articles published in the Canadian Journal of Pure and Applied Science for the latest 15 years. The CJPAS authors relate to all the geographic North and South America, Europe, etc., etc., Russia, the Pakistan, India, since 2007, 641 high quality papers, uh, reviewed journal, peer reviewed journal, on average 43 papers annually, 15 papers, sufficient acceptance. So I can, yeah, so you could paste that. Can you paste your paper or your article in there like that? Maybe we can see like that.
I hope it will be published in the following issue by the Canadian Journal in February. In 4 months.
Okay.
And,
so if you can paste some of the copy and paste some of the material, we can probably see what, you know, when you're talking, we can see that.
What's your conclusion? Is it more of a study, or are you trying to find something out?
I have discussed that the most contributions are made to this journal by such countries as Nigeria, Pakistan, India, the United States, Canada, Russia, the United Kingdom. And because you know that Nigeria now, it is slightly discussed, Nigeria now has very large planes to put astronauts to space, to develop space technologies, cutting-edge technologies, and you see that many sources from Nigeria are published in North American journals like Canadian Journal of Pure and Applied Sciences. You have to know that in Nigeria there is the English language as an international language between the Nigerian states. They speak in English.
Okay.
And I have found that each third paper is published in this journal by 4 authors and more. Each third paper. Maybe it is right for any journal or majority of journals.
Yeah.
And each third paper is published by 4 authors and more. And also something, the acceptance duration between the submission of a paper and the acceptance day is more than 2 months. I have found it is by about 67 days on average.
Pretty good.
If you submit your paper to this journal, on average, you can have answer about acceptance in 2 months. It is okay because the journal is published for monthly.
Yeah.
Only 3 issues every year, in February, June, and October, and 2 months consideration. It's okay for this journal. Maybe some journals consider articles for 2 years or more. I don't know. For example, in one paper, probably in Singapore, my paper was under consideration for more than 2 years. I have forgotten already that I have submitted this paper to this journal. It is crazy.
Yeah. And are they ever going to get back to you, do you think, or? Aleksey, what country was it? Singapore? Do you think they'll get back to you about your paper? Maybe not.
it is statistics on this journal, and I have demonstrated about the authors from which countries, and it's about many African countries, many European countries contributed. Authors from many countries contributed to this journal already. It is an international journal, isn't including you, when John from the United Kingdom, and me from Russia. And it is natural that
this is our paper. Yeah, I mean, I want to briefly show the circuit.
Yeah,
right? So this is a circuit I'm talking about. So now you can see that. Yeah, this consists of the electrons, monopole, and the positron. They form like a clock circuit, caught-up circuit. And we analyze this one. This is the paper that's going to be published. They accepted it, so it will be published in a month or so, I think, hopefully. So all the Hamiltonian, everything we did, and we say that it's like Susie, you know. So it's like Susie. And then because there is a asymmetry of the North Pole and the South Pole, then it will act like, asymmetric string matrix gauge. So that's one of the conclusions. So then we came up with the more analysis and then find out the table, the schematics, how it works. And finally, we different schematics. See here, when you look at the last one, so Christopher also drawn this one. So we found that this is the most useful one. So here, the dipole magnetism, it can act like a gluon. You see that? So this is because the Gauss theorem, automatically they form dipole almost naturally. So they can form and can produce a gluon, act like a gluon. So it may explain gravity, I think. And these are electrons, electric field, the positron electron field. So it can rotate around that, it can spin and all that.
Can I ask, Torsion, you say it acts like a gluon, but aren't gluons, they're there to bind like up and down quarks in the nucleus?
Yeah, so this can act like that in the sense that they can act as separate, but also they can come together. When they come together, they can, they can produce with the electron positron, they can produce quark and also gluon, I think, depending on the media.
Well, yeah, I mean, if they're producing quarks, they're producing gluons, right? Necessarily, because quarks can't exist.
No, they are separate. The medium has to be different, mediated by, it has to be mediated. For example, electrons and positrons have to be mediated by a photon to produce a quark, right? The photon will mediate electron.
You can have W bosons can be in the mix there. Yeah.
Yeah. So it's like that. So it depends on the mediator. So depending on the mediator, for example, this North Pole and South Pole, if there's a right type of mediator, it can produce gluon.
Hang on though, but like as far as I know, I could be wrong about this. Correct me if I'm wrong. The only time I've ever heard of quarks being created, like matter being made, is in like a flipping, what do we call it, a particle accelerator, like the LHC, where they basically they just ram loads of particles at a disk.
Proton and proton bombardment, for example.
Right. Yeah, it's really difficult to do, and they just keep doing it, and they're basically pushing so much energy in, and then you get these jets of matter and antimatter.
Yeah.
And that's basically what they're doing, is they're stretching that rubber band of the kind of quark confinement. And each time they do that, it releases a quark pair with a gluon obviously in there somewhere, but they're never separate. So but the energy required to do that is huge, and the difficulty level is massive. I'm just wondering, how's your circuit doing that?
Or the naturally, because it can, what we are saying here above is that it can occur separately and they can join together. So they can act as functors.
Yes.
So they're separate. And then like a functional is like a mediator, something like joins them together, and then they can act like this one. They can produce a dipole. So they can exist as monopoles, and then they can combine as dipole immediate, when they're in the vicinity, when they are brought to the neighborhood.
If that rotates or something, it can.
Yeah. So it's continuously rotating.
Oh.
This is rotating. It's spinning. Each one is spinning. The electron is spinning. This is rotating and also revolving. So three things are going on. We are going to find out. I have written some Hamiltonian spherical coordinates, and we'll discuss that. But I think something you are trying to simulate in the computer programming.
Yeah.
Last time we can start doing that. That may be a good start. Only thing you said it will take like 3 or 4 months. That's okay now, because our paper.
It's great. The rotation thing I can do. What I need from you in order to do that, Rajan, is it possible for you to scroll up to the PDP circuit, the Helmholtz? I'm not saying that right. Helmholtz, the matrix, or the maths that describe that. I believe this is it, isn't it? This schematic of the circuit.
Yeah, that's a basic circuit. Yeah.
Right. So there's and if you scroll down, there's a more mathematized version of it.
This one.
This one, yeah. So you're going to be putting tensor products and all sorts of things in there, I take it?
Yeah.
And so what I'd need in order to do, like, are you able to differentiate that with time? With respect to time.
Okay. Differentiate this with respect to time.
Yeah.
So
that's how my simulation works. It can only be. I know with relativity, they can be background independent. Is that right?
Yeah. This is one of the things that you get. You mean this, like this one?
Can you use time in this circuit, or is time? I mean, it's quantum, so quantum is.
Yeah, there's another one where I put time evolution. I can look into that. I think.
Right, because I'm going to need that obviously, because I can't animate in order for us to,
there is also a differential equation.
Yes.
Partial differential equation where that one is a gradient, so it is a space differential. But there is another one, I think, time differential. I can look into that. Yeah. Right. You want the time differential, right?
I'm gonna need that, because that's how all of the simulations that I make on the computer are based. They're all just time differential, which just means that there's a small moment of time passes and something happens in that moment. And that's all that means. So
dynamic action.
Unless you give me the equation in a form similar to that, I can work with that once.
Okay. And there is another one I am developing. Maybe I can share that also, where that one is actually, let me see. I think I have it somewhere. I have to share with the. I don't know. You can see that.
You can see that's actually one part of my animation there of like a spinning. I was telling you about this once on the spin 1/2 particles. So it's a Clifford rotation. So when you rotate that object twice, it it comes back to its original position. And usually, I think was it not Dirac, but I've forgotten his name. The Klein equation, and then you had the relativistic version. Yeah, Dirac, and then you had the Dirac equation and the spinors. And you have like space-time twisting, and it's all very complicated. Spinners, they're called. So I just think that this is like a much simpler method. The only thing that this wouldn't be able to explain is it Majorana particles that can spin in both directions at the same time. Like they have no right or left spin. So this is my feeling. Like I'm just trying to make things simpler because that's how I roll, kind of. But so I suppose it's kind of similar in the sense like of like expanding space-time. Here I'm sort of removing twisted space-time. It could still be a part of the theory, but it's more how do you say? This is like just a simpler model to work with inside a computer, so we don't need like all of these fiber bundles twisting around and getting really messy. Just keep it simple. So like obviously this particle looks like it has a three-dimensional extent, but that is purely for simulation purposes. It's like otherwise we will be working with nothing. We have these dimensionless particles that have no extent, but I mean if you can't see that, so that's kind of the basic concept. Okay, Rajan,
okay.
Go ahead there. Sorry.
Okay. Yeah. So essentially that's what. So I have an equation. I can actually send to you. I have worked out some equation. Okay, this is the estimated size of the particle. But what I have written is a Hamiltonian of the spherical coordinates, and it has a theta rotations, like we said, theta, phi, and gamma rotations, rotation and revolution and all that. And I put all this together, and then I'm trying to solve that 2-dimensional versus 3-dimensional versus 4-dimension, trying to put them together. And so it will automatically have time aspect because it has angular momentum, omega, which is dou theta, differential of theta with respect to time, right?
Yeah.
That's what omega is. So it will automatically have time aspect.
Okay.
I think that may be useful to you because the rotation in time, which is angular momentum, right? And that angular momentum you can change to energy because h bar omega is your energy. So I think we should be able to work with that probably.
Yeah, that'd be no problem. I was just making
and then you can connect with your Clifford rotation. You can try to match them, make it compatible. And I think that's what I'm tried. And I worked out some things I can send to you, and then we can work out more to make it more computer, algorithm for your computer.
Oh yeah, no, I mean, as like if you provide it to me in a specific way, I can do it very quickly.
Yeah, I will send what I have. Then you can tell me what else you need to start the programming.
Great, yeah, because I need quite a bit. Just yeah, I will I'll draw up a list, but it's basically like maybe a range. That's not that important.
Yeah, I will send out my workout, and so when you go through that, you know what I should modify, what I should do further in order to make it more computer programmable.
Okay, right. So I can start working on it as well from.
In a week or two, I'll probably next week. I think I have some corrections to do the other papers. I already sent some old thing. Because send some papers, but I think next week I should be able to send. By next weekend, I should be able to send you before next weekend, I think.
Right, Rajan, by the sounds of it, you've got three. How many things spinning? How many objects in total? There's about 4 objects, and then there's
each particle or monopole, they will spin, right?
Yeah. So
and the whole circuit will rotate.
3, 4.
Right? Yeah.
3.
3.
Because the monopole is 1. It has 2 particles, but they're 1. Okay.
Yeah, the monopole. Yeah, there are 4 of them, right? The north pole, the north one, south one, the electron, the positron.
Yeah.
So there are 4 of them that can spin.
Oh, so it's four. Yeah, it's four,
Yeah,
and then
four.
the whole thing spins.
Spins, rotates or whatever.
Yes.
And there's a revolution also occurs because these like form one cell and another cell, right? So
Yep.
they can revolve around each other like that. So
So are they completely free to move wherever they want? Yeah, of course.
I would think so.
Yeah.
I think it'd be like a superfluid, like Dr. Zong was saying or Aleksey was saying. It will be very similar to superfluid situation, I think.
Okay. Yeah, because I've been thinking about this completely differently. So that's going to be pretty complicated too.
Yeah, I'm trying to use this Hamiltonian may make it easier, and we will start with a simpler thing, you know,
Good.
and
Yeah.
then we will add more complexity to it. But we'll start with a simple rotation, spin or rotation, and then we'll add more complexity, you know. So we build up the the model.
Well,
I
like
think
think about
that's
it this way, Rajan. You know this idea of like finite group rotations.
oh
I'll have to think about it.
okay
Put it in a way that'll make sense to you. But like, if you have two electrons, yeah,
uh-huh
and you rotate one 360 degrees, which is really 720, then that's okay. But like apparently they say that if you were to switch them like this,
uh-huh
it's equivalent to rotating
oh yeah
one or both like that.
yeah
And that's because one is sitting in an electron shell,
yeah
higher energy. So when
yeah.
they change places in the electron shell, it's equivalent to a rotation. And
Yeah,
that's
actually, the simple harmonic motion, I think that Dr. Zong also is working on. The simple harmonic motion, you can convert this back and forth movement is same as the rotation. You know, the pendulum that swings like that is same as a rotation like this.
you
It's
see.
it's an analog, it's an equivalence.
Sorry, the reason why I bring it up is because in my simulation model,
Yeah.
that doesn't happen. Like if you were to like that's in my understanding, that's a purely I hate to say it, it's not a fudge, but it's an interpretation of events or something, and it's only applicable to the energy states in an electron. That's as far as I see it anyway. I could be wrong about that, but I find it interesting that idea of something moving back and forth being equivalent to a rotation, though.
Yeah.
That's not impossible to simulate. Like I could totally do that. I can have the particle moving forward and also rotating.
You can kind of think of the mechanical thing where you have a wheel, right? And you have an axle that goes back and forth, and it converts to a rotational motion.
Sure, yeah, that's no problem.
So it actually just moves back and forth, the piston, but in that movement, because of the you have the axle, the what do you call that converts to a rotation. So it's very similar.
Yeah, of course. That's not a problem really. So I think we should start. I could probably start doing some simulations then.
And then I can supply you this one, and we can work on that, and then incorporate this one. So make it a little more realistic, but it becomes more complicated. But we'll stepwise we'll add the complexity.
If I can just say, like, let's say imagine you have 4 planets, like roughly equal size, and they're all spinning.
Yeah.
And are they also, what are their orbits? Are they going around like this?
Yeah.
Just every way.
Yeah, everywhere. Yeah. So we have to isolate each one based on XYZ axis.
Yeah.
So we'll say, okay, x-axis what is rotating, y-axis what is rotating, z-axis what is rotating.
Technically, you can't, with the quantum systems, like you can't say the thing is there or here or wherever, but it's kind of everywhere.
Yeah. That's the problem with the quantum system, that it can there is no particular, because of the vector quantity. I think it's because of the vector property.
Yeah.
That vector, if I put it here, it's the same as another place. The vector automatically translation. The translation is an automatic thing.
Right. I mean, there's loads of interpretations of why that is, and they're all very interesting. But generally, it's considered like a limitation on trying to do what you're suggesting, which is having like little balls going around. Like, what do you think about that?
Yeah, I think we could start with that and then add this complexity, because we have to start with this basic, but the basic system has to be flexible. That we can add complexity to. That's the only requirement.
Raised though, like the first thing is like, Schrodinger's equation is great and all, but like, let's say, we could imagine that maybe there is a position where the particle exists,
Yeah.
But just because we haven't observed it, so it's in lots of places, doesn't mean that it is in a specific place when it is observed.
That's what Einstein was really, challenging.
Yeah. I mean, I follow that. Like, so it's in like, like once it's observed, we know it's in a specific point.
Yeah.
For all intents and purposes, it was always in a specific
the
point.
quantum non-locality, whatever they call it.
Yeah, I mean, it does funky things in the meantime, but it still has like a general position.
I think this is the nail in the what you call is the this is the what you call, this is the whole deal. I mean, this is the main point of the quantum mechanics. I think we are talking the link between the quantum mechanics and the relativistic thing. What we are talking is very, very much touching on that.
Yeah, I mean, I follow that. I had something else to say about that issue. Schrodinger was good, but yeah, sorry, it's I've forgotten it.
Aleksey also has something posted.
Does he?
About a research gate something. He has posted something.
New messages. Ah, great. So did you just uploaded that? I take it, Aleksey. So you can you're sharing screen. So whenever you want to share that, you can. But was there something else I was going to ask? Functor, function, and functional. Yeah.
Oh yeah, that's an interesting thing. I think that's something we are going to look into, because I find that to be quite useful in the sense that
can you
the functor?
Can you define functor for us? It's a category. It's a function that has
categories.
Yeah.
Functor is a category. So this separateness. So one functor is here, another functor is here, right?
Yeah.
Okay. The only way they can interact is there has to be a functional that connects them, like time or something.
Okay. So can you define a functional? Oh, functional is like time. It's like
like function. Yeah, something that links it. A link.
Okay. Yeah.
And then inside each functor there is function. Something is happening, like our circuit is clock or something is going on. So that's a function. So you have function, and it is inside a functor, right?
Gotcha.
And there are functors like that, separate entities or separate cells, and these functors will act separately. This will act separately. This will act separately unless they're connected by a functional. Which is
and this is your finite element.
Yeah.
So the node or the cells and the lines connecting them.
Yeah.
But you don't say nodes and edges or.
Yeah.
Yeah. So it's interesting. I mean, it's totally bizarre.
Yeah. But I think for me,
loop quantum gravity though in the cell-like nature of it and the clocks and the event thing, there's an awful lot there that's very loop quantum gravity, yeah?
Oh yeah. I think quantum gravity, it connects with all that, I think, eventually. So I think everything should come together, my feeling. But I think the most useful, the functor thing is going to be quite useful. I mean, those kinds of things are going to help us to figure out. Okay.
Sure.
Yeah. So Aleksey is still there, huh? Is he still
Yes.
there?
Yeah, I'm here, and if you look at your chat, you
Yeah.
can see the link to my
Oh
paper.
yeah, I uploaded the link. Statistics on the papers published the Canadian Journal of.
Yes, and you can read it. You can see
Okay.
the statistics I mentioned.
Okay. 43, the statistics.
Probably you can show this paper on your screen in order that we can see, because I can't show on my screen and to share with you.
Yeah,
I
yeah,
don't
yeah.
and
I
you
can. Yeah, I am able to pull up that. Yeah, it says average duration. It says about the database, chemical abstracts, impact factor. Then you have
That's all.
volume. Okay, astronomy. Yeah, actually, we also we may want to publish some things as things go on, but myself and Chris also.
Do you want me to share it, Rajan, or can you share the screen?
I can try to share.
If
Let me
somebody
go up.
can share this paper on the screen.
Yeah.
Yes.
Yeah, already. Yeah.
What about that? Can you guys see it?
Yes,
Yeah.
I see.
Cool.
This is, yes, it contains 7 tables
Aha.
with
I
the
got the scroll.
statistical data.
Right.
The first table, you see, it's concerned with the volumes, issues, and how many papers were published in each issue, and therefore in each volume. In the first column, you see the volume, the year, and the total number of published paper in the volume. And in the third column, you see how many papers were published in each issue.
Uh-huh.
It is for the last 15 years, or for the first 15 years, for all 15 years.
Uh-huh.
And in the second table, you see the countries, the authors of which have already contributed to this journal. It is in the alphabetic order, and you see many countries from Africa, from Asia, Europe, European countries. You can see Switzerland, Swiss, Turkey, Greece, France, Germany, etc. And even Fiji Island
Great Britain, lot of
have contributed.
Great
It's
Britain.
at the top of this page. At the top of.
Oh, so which page? This page?
Yes, continue. Table 2, continue. You can see that Canada, the United States have already published a lot of papers in this journal.
But Nigeria is the top one. Go ahead.
And you can see the third table on the next page, probably. The third table, it's about the databases. You have to know that the Canadian Journal of Poor and Applied Sciences is indexed in the oldest well-known and reputable database, such as the Chemical Abstract Service. This CAS service was established in 1907, more than 100 years ago.
Oh.
But it has no impact factor because it is only specialized on chemical and relevant subjects.
Yeah.
And we have only 2 databases like Scopus and Web of Science, which assign impact factors for journals.
Yeah. Can I just say something there?
They're not old, they're new databases.
Okay, yeah, Scopus and this are new.
You see that the Web of Science was established only 5 years ago.
Okay.
It is British.
Yeah, you know the way if you were to publish this in the Canadian Journal and then you were to say you were to upload it to ResearchGate and then put in, it would ask you for the name of the journal. When you put it in, it just like rejects it. It says like, oh, that we can't find that journal. It's not listed.
Yeah, I met this problem as well.
Yeah. So obviously it needs to be part of some recognized body, but it, you know, I just think it's interesting that it's listed in these databases that are recognized, but it doesn't seem to be recognized by ResearchGate.
By researchers. I don't know. ResearchGate has its own database. In general, it includes journals indexed in both Scopus, Web of Science, maybe in PubMed, maybe in chemical abstract services. For example, such the United States journals as Hadronic Journal, which is a very old journal.
Yeah.
It is not indexed in Web of Science or Scopus, not in CAS, not in the PubMed, but it is it present on the ResearchGate, in the database of the ResearchGate. This journal, it is different. These all databases are different, and they have their own politics to include titles of journals in their databases. For example, there is Pablon, such service for authors and journals like Pablon. The Pablon, you know Pablons.
No.
Pablons, yeah. Scopus.
It is a part of Clarivate Analytics, and the Web of Science is also the part of Clarivate Analytics.
Okay.
And Pablons only use the database of the Web of Science, not the database of Scopus. But the ResearchGate uses both the Scopus and the Web of Science databases and the other journals which are not included in these databases. They also present in the ResearchGate databases of the journal.
That seems a bit contradictory, doesn't it? Because if the Canadian Journal is present in Scopus and ResearchGate uses the Scopus database, then shouldn't the Canadian Journal be recognized by ResearchGate?
Probably, I don't know. But now, several months ago, I have applied for the Scopus for this journal, Canadian Journal of Poor and Applied Sciences.
Right.
It was said to me an answer letter, try anew, because there should be on the website of the journal some additional information. It should present. It is now absent, and they can't consider. They have written to try a new year, and I have written this paper about the statistics for the first 15 years, just for probably it will be useful for the authors of the journal and for the Scopus, for reviewers of the Scopus, because they combine such analytics on a journal. How many authors from which countries? For example, it is good for a journal that each issue is published just in time. For example, the February issue is published in February or maybe earlier. The Canadian Journal for Applied Sciences publishes each issue just in time. If it's February issue, it will be published in February or even in January. It is okay, but the Canadian Journal for Applied Sciences has no DOI, digital object identifier for each article. I don't know why, but however, they said in this Canadian journal that they have put all issues on the Canadian databases, which is called the Library of Canada, and they don't need DOI probably, I don't know. Maybe they will buy a DOI domain, maybe not. It is just the politics of the journal. I'm not familiar with this politics. I just combined, for example, table 7. You can see how many papers are published by single author, by 2 authors, by 3 authors, and by 4 authors and more. You can see that the most papers, every third paper was published by 4 authors and more. I don't know, is it a common situation for majority of research journals or not?
I think so. I would say so. No, you always see like papers and there's like multiple names. Like look at this here.
Yeah, like this, you see a lot of 10, 11 authors.
Yeah, you can have like, I've seen like 60 authors on a paper and just ridiculous numbers.
Yeah.
I have cited one paper by Nobel Prize winners. There are more than 1,000 authors.
And they're obviously not all contributing.
I have put all authors and in the paper submitted to this journal, Canadian Journal for Applied Sciences, and they have answered me that not more than 10 or 15 authors can be present, can be shown. The only first up to 15 authors can be shown in the references. So
wow.
Some journals show only the first author, and then they use et al. Do you use the Brave browser?
Yep. This is the new edition.
Yeah.
The new issue,
you just opened the paper by Zamsha.
This is the one I'm interested in, yeah, because I had a few questions about your presentation last week, Aleksey. Can I ask them? I was going to ask you.
Yes, Zamsha is from Australia. He now lives in Australia, and Shevtsov is from Belarus. And Zamsha is a former student of one very old professor who worked for some laboratory like Livermore laboratory in the United States, something like this.
Okay.
This laboratory has created the United States nuclear bomb.
Right.
And he worked for similar Russian laboratory for many years. He was the head of laboratory. Now he's very old, and Zamsha is his former student, and they are called torsionists because they work with the torsion field.
Yeah.
And this is the so-called forgotten field because it is only used in the theory of gravito-electromagnetism. The theory of gravito-electromagnetism is a pure gravitational theory without electrical field, without magnetic field. In this theory, the gravitational field is called the gravito-electrical field, and the torsional field is called the gravitomagnetic field. To have an analogy with the electrical and magnetic fields, because in the theory of the electromagnetism there is only these two fields, and I treat all fields together: the electrical field, the magnetic field, the gravitational field, and the torsional field. The torsional field is also known as co-gravitational field. And so it's for solid. This paper is for solid because and you see a lot of material constants there just for solid. For a vacuum, we have not many. Okay, we don't treat piezoelectric constant for vacuum. We don't treat piezomagnetic constant for vacuum. Piezogravitic, piezocogravitic constant, it is piezotorsionic constant because Yefimenko is called cogravitic instead of torsionic, and torsionists say this cogravitic as torsionic. They say torsionic, and these last four constants, it is very important. Here it is shown in the physical dimension in kilograms, second, and meters, and you see it is basic dimensions. It is for a solid.
Right.
So, but these four last constants are for a vacuum as well, and I use subscript 0 for vacuum constants, and without any subscript for a solid.
Okay, but in total there, sorry, can I just say in total there you've got about what, like 16 U waves or something? Is that correct?
What do you mean 16?
I thought I read somewhere in the paper that
Here, yes, you can see. It is shown. You can see in the paper that the speed of light CL with subscript L is equal to, it is a well-known formula, epsilon 0 mu 0 power minus 1 second. It is 3 by 10 power 8 meter per second. It is well known. It is approximately.
Oh, it's a Maxwell.
This is the speed of light.
Yeah, Maxwell calculated.
Yes, the exact value of the speed of light was measured exactly only in the 1970s, 50 years ago. We use now.
the point I'm asking though is
Yes,
you have like you have all of these waves. Yes, exactly. I'm asking what are the sources of these waves? This radiation, like, are they all man-made? Are there any natural sources?
Yeah. For example, if you excite electromagnetic waves, they have both the electrical subsystem and the magnetic subsystem. you also excite simultaneously. It is also simultaneously excited, can be excited both these two fast waves, the propagation of which certain order faster than the speed of light. Because you see that the electromagnetic wave have two subsystems, and these two new waves have also these two subsystems in addition to the gravitational and torsional subsystems. If you act, for example, to excite an electromagnetic waves, if you act on an electric subsystem, you excite right away, can excite right away three waves, electromagnetic, and these two fast waves, the propagation of which 13 orders faster than the speed of light.
Yeah.
However, you have no good detectors to detect them.
Although this guy here,
for example,
something.
Kozyrev have observed. I have mentioned last time. Kozyrev have developed with one researcher. They have developed tools, non-optical tools, to observe right position of the stars on our sky, on our skies, because what you see it is an optical illusion, because you have to know that on the skies you see right away the stars distant from us on 10 light years, on 100 light years, 1,000 light years. What you see, it is illusion, simply illusion, the position, because you can see near each other one star distant from us on 10 light years and distant from us on 1,000 light years.
Yeah, I think
and
we will understand that. But I'm just
if you use optical tools, it is you see such illusion on our skies.
Of course.
Kozyrev has because it is very slow the speed of light for the cosmic scales. Kozyrev have developed, yes, it is Zamsha is developing his own devices, is improving them. His experiences, he works already for decades in such area, experimental area, and he's show me the end of the paper before references. You can open the second paper by Zamsha and you can see the warning, because this is dangerous. Open please the second paper by Zamsha.
Oh yes, the magnetic scalar field generator. If we go down just before references. Warning.
Okay, yes.
Please take precaution when use a big power scalar gun, because its operation can harm your health. I'm not surprised, because like scalar
general dangerous radiation, and you have to be careful with such things. I have said that the population of 4 institutions of the Soviet Union, of the former Soviet Union, were died due to this radiation before they have understood the reason why they dead.
Oh yeah.
Due to this radiation, because these 4 institutions were studying these things. And anyway, it is developing. The devices are miniaturized. You can see. you can find many devices in the internet, or this result he has put on Achieve, the American system. I have spoken with the professor I mentioned, Shkatov. His name is Shkatov, and Zamsha is his former student. And Zamsha has a book, probably it is cited in the references. Show me the bottom of this book. Yes, this book, Shkatov and Zamsha, about the torsion field. And it is the problem is in Russia. I have to say that Kozyrev has developed his theory concerning this phenomenon, that he has observed the stars at the right positions. He thought that it is the phenomenon of time, it is the effect of time, not the wave propagation, because the wave propagation means the phenomenon of both the space and time. You see that velocity is a meter per second, but not only second, only time, because he observed the signals from the star distant on 1000 light years. He observed at the right positions. What he did, he first of all he observed a star distant from us on 1000 light years using an optical tool. Then he has calculated the right position on the skies of this star, because in 1000 years this star will have another position, right position, and he used this created by his team, this non-optical tool, to see this star at its right position. And also the groups which study torsion field, the torsion field are called in Russia torsionists. And because they follow, maybe not all of them, they follow the work by one Russian Soviet Union researcher who thought that there is only one single torsion field instead of 4 fields: electrical, magnetical, gravitational, and torsional, because all the other 3 fields, electrical, magnetical, and gravitational, can be written independence on this torsional field. It is Shipov, yes, the theory of Shipov, Akimov and Shipov. Their work is not well accepted by the research community, and because I explain why. Because you see that in the electromagnetic waves we have the electrical subsystem coupled with the magnetic subsystem, and nobody says that there is only one electrical subsystems, because the electrical subsystem is coupled with magnetic subsystem, and the magnetic subsystem can be expressed in the dependence on the electrical subsystems. What Shipov did, he has found that these 4 subsystems are coupled: electrical, magnetical, gravitational, and torsional. And because they are coupled, and this means that all these 3 subsystems, electrical, magnetic, magnetic and gravitational, can be expressed in the dependence on the torsional subsystems. And therefore, there is only torsional subsystems. It is questionable, and I don't agree with it, because you see that the electrical and magnetic subsystem in the electromagnetic waves are also coupled, but nobody says that there is only the electric subsystems, because the magnetic subsystems can be described in the dependence on the electrical subsystems. So they are coupled. Indeed, in the electromagnetic waves, there are two coupled subsystems such as the electrical and magnetic ones. In the gravitational waves, I have to say here that I prefer to call the gravitational waves the gravitatorsional waves, because there are also two subsystems, the gravitational and torsionals, to propagate for the gravitatorsional waves. They are called the gravitational waves. It is they forgot to say torsional field, torsional subsystem. So, and I don't know why they forgot. The torsional field was introduced by Cardano, who worked with Einstein more than 100 years ago. And it is a forgotten field, torsional field.
So it is not a space-time warpage, is it not? It's completely different, or is it exactly the same?
Between
space-time warpage and torsion fields, are they equivalent? Are they similar?
Space-time is coupled with the propagation, with the speed, because speed is meter per second, isn't it? It is space-time.
Yeah.
But in order to demonstrate that some subsystem can propagate, for example, the electromagnetic waves can propagate with the speed of light, you treat both the electrical and magnetic subsystems in some way, and you have some equations leading to the propagation velocity. Is it understandable?
It is the propagation of the wave velocity, did you say?
Yes, wave velocity. Yes, the propagation wave velocity.
You mentioned that before, I think.
If you treat all four subsystems, you can construct some model, some equations which lead to some propagation wave speeds corresponding to the wave motion in which all four subsystems are participated, like gravitational, torsional, electrical, and magnetic. It is how do you treat your problem? Do you treat only two subsystems, electrical and magnetic, for the electromagnetic waves propagation, or all four subsystems for if you treat all four subsystems, actually you will have four waves, such as the electromagnetic waves, the gravitatorsional waves, plus these two new fast waves, the propagation of which, the speed of propagation of which is certain orders faster than the speed of light. This, if you complicate your model, if you include both the gravitational and torsional fields to your electrical and magnetic fields, you actually will already deal with these four speeds in a vacuum.
Okay,
if you treat only two subsystems for vacuum, electrical or magnetic, you will deal only with the electromagnetic waves propagation.
Yeah. Okay. So what do you think about like natural sources? Do you think like, you know, ley lines and energy coming from the earth, and is that related? Like, there'd be torsion fields throughout the earth. Can we detect them? You know, can we detect them physically without, you know, like divine, you know, housing?
Yes, it's a good questions. Indeed, this team, Zamsha, Shkatov, they have some researchers situated in New York of the United States.
Yeah.
One in Australia, one in New York, one here near Krasnoyarsk in Tomsk, and they have constructed some detectors and generators of these waves. First of all, these waves were generators and detectors of these fast waves were created using money by KGB. You know KGB, the Soviet Union KGB. KGB has delivered, has given much money for creation of this. Do you know KGB?
No, I've never heard of them.
Soviet Union KGB. KGB, it's like Me-6 in the United States, in the United Kingdom. Me-6 or Me-2.
MI6. It's KGB. Yeah.
Yeah, KGB. Yes,
Yeah.
KGB.
The intelligence, secret intelligence groups, special agents and secret intelligence, right? KGB. It's not called KGB anymore, though, is it? It's called something else. See, these are kind of like old-fashioned torsion devices, if you think about it.
Is a torsion connected with the vortex action?
Yes, it is coupled. The torsion field is also called the spin torsion fields because it contains spin. It contains vortices, rotations. It is coupled with rotation.
Vortices, yeah, vortices.
You see these guys, this schematic, where they walk up and down and then they locate like points on the ground which have energy in them. And I think that's kind of interesting because usually
like dowsing.
Yeah, this is a book on dowsing that I bought just one day. But we were doing I actually work with a group of people who do this kind of stuff regularly. Like, I take them out, and what we do is we walk around with detectors like this.
Oh, you have that?
Magnetic detectors, and we detect anomalies on this mountain that's nearby my house. It's an extinct fault line, and so there's an electromagnetic anomaly up there that attracts birds and all sorts of strange people as well. And
is it like a Bermuda type?
Yeah, it's like a smaller version of that, I suppose. And so there's strange things that go on up there, and but what you can do is you can just walk around, and if you're you just sort of clear your mind and relax, you can start to feel different points of energy, and sometimes it's like a magnetic force pushing against your head, and we call that neutral. And then there's another one that's like really positive and makes you feel kind of like as if the energy in your body is all unified, it's all one. And so we'd go around and we'd mark these different points with different bits of string. So red for yellow for the neutral and blue for the positive. And then one day I was out with a couple, an Irish guy and his wife, and they found a negative energy source, which was in a valley. It was like, I wouldn't say a valley, but like a depression, and the ground went down. And then in the center of the depression, you could stand, and you could, if you just stood there, you could feel like this really like chaotic energy. It was like like this all the time, and it made you feel really ill. And so
it's enervating.
Enervating, yeah, that's a good word. Yeah,
saps your energy, right? Sap.
Very a disparate kind of energy, diffuse, and made you scattered your thoughts and all of the rest of it. So
Disoriented. You become
yeah.
disoriented.
So like I think
it is also said that maybe you know such words, the third eye.
yes.
The third eye. If
Yeah.
you close your eyes, yes, this third eye is a rudiment to feel this four-field radiation. We use our eyes to feel the electromagnetic waves, light,
Yeah.
only in narrow diapason. And the third eye can feel this four potential four-field radiation, maybe also in very narrow range of frequencies. And this is the rudiment we have still. If you close your eyes, you can see some maybe slightly light by your third eye, and it is said that this third eye can feel this four-field radiation. There is such opinion. So
Torsion. You mean torsion
humans
fields?
have such rudiment.
Yeah, this is kind of what I'm asking, Aleksey.
Rudimental sensor.
Do you think that these extrasensory energies, they are the torsion fields? Yeah.
Four fields, not torsion fields. It is four fields coupled. This radiation represents all four fields, not only torsion fields. But Shipov thinks that there is only torsion field because the other three fields can be represented independent on this single torsion field, and his theory was not well accepted by the research community. I repeat that we don't say that there is only the electrical field in the theory of the electromagnetism. We say that there is the electrical field and the magnetic field, and here the same. We should to deal with four fields: the electrical, magnetical, gravitational, and torsional, all four fields, but not only. It is not good to say that there is only a single torsional field by Shipov. It is easy for us to have this the single field, but they are all four fields coupled together. And this radiation, these waves 13 orders faster than the speed of light represent the coupling, the wave motion in which all four fields participate.
Aleksey, do you think that a person can manipulate these things? That we
That's a good question.
Human being can manipulate this.
Could you repeat your question?
Okay. Do you think that human being can manipulate these fields?
Who can manipulate these fields?
A person, any person, like you or me.
It's a good question. This team by Shkatov, Zamsha, they have published one paper that they can put some radiation in some direction, for example, to you, and you will die.
My God, the gamma radiation.
Or some change in your health will be found. I don't know.
Okay, yes.
Maybe it's dangerous, maybe not. Is it true or not? And they, because you see that this speed is 10 power 21. This speed is enough for a single to cross whole our universe for millisecond. This means that if such radiation is created, it is traveling in our universe forever, and therefore you can record, you can using some tools you can find this signal from the past, for example, and to see what was in the past.
Oh.
If you find this signal, and if you can construct some tools to select some signals, you can see what was in the past, because such signals are present, are radiated by any body, and it is recorded. These signals are created and they exist forever in our universe.
Right. What
Do
about?
you think aliens can use this, or can we find aliens by detecting these signals?
Aliens.
Yeah. Can we detect aliens?
If aliens exist, they don't use optic systems to communicate between, for example, even neighbor planets or neighbor stars or neighbor galactics. It is impossible to communicate by optical
but torsional.
systems. It is crazy. Even with Mars, with the planet Mars, we have horrible things to communicate because there is a delay of from 8 to 20 minutes.
Yes.
It is horrible to communicate using any optical
But
device.
what do they use? This fast.
They should use this communication system based on all four fields. All four fields. You have to treat all four fields: electrical, magnetic, gravitational, and torsional, to develop
Can you combine them?
this gravitational engineering. It is already relates to the gravitational engineering.
Can you combine all the fields together?
Sorry?
Can you combine the fields?
All fields? I have combined all. I have treated all these fields, and I have obtained these two fast speeds, because I have considered all these fields, all these four fields. This is my finding of this. My findings of these two fast fields. The propagation speeds of which 13 orders faster than the speed of light is due to the fact that I have combined all these fields: electrical, magnetic, gravitational, and torsional.
How do you do that?
All four fields.
How
In
do you do
addition to the fifth field, you see that you have known that there is the fifth field. It is called elastic field. If you treat a solid, you have to treat all five fields: elastic, electric, magnetic, gravitational, and torsional. And
how do you do that? How do you combine?
Have I combined?
Yeah.
Together these four fields?
How? What device, what technique did you use for that?
I have constructed a model, mathematical model. Mathematical model which includes all these five fields for a solid: elastic field, electric field, magnetic field, gravitational field, and torsional field. All five fields. In a vacuum, only four fields should be treated.
But
Electrical,
you have a
magnetic,
device
Sorry,
A device.
devices.
Yeah.
Zamsha is one of teams which construct different devices. Even I think that Tesla has constructed many devices which were based on all 4 fields, but that time they did not know it. If you know that Tesla has constructed one motor for a vehicle, this motor, he has said that this motor is harvesting energy from the space, from the universe, not from the star.
0
Because
point.
if a motor, if a vehicle, if a device is harvesting an energy from the universe, it's all 4 fields. If from a star, it's only 2 fields, electric and magnetic.
Yeah.
For example, if you use solar cells, these solar cells are harvesting energy from our sun, for example, and from light. But light.
What about you, though, Aleksey? Would you consider yourself a theorist or an experimentalist? Do you have machines that you work with, or are you mainly theory?
You can see these 2 papers by Zamsha. If you see torsional field, if somebody works with torsional field, and the paper tells us that this is due to the torsional field, this means that all 4 fields are taken in account. All 4 fields should be taken in account. But some researchers believe that only one torsional field instead of all 4 fields, electrical, magnetic, gravitational, torsional, only one torsional field should be treated. It is by Shipov, this opinion, by Shipov. If you see that somebody tell us that this device relates to torsional field, you have to keep in mind that probably all 4 fields participate in some. However, if you have to measure only torsional field, it is possible to create some devices. Probably for our planet, the Earth, the torsional field was measured.
And our mind can convolute this.
The torsional field can be separately measured like the gravitational field, like the electrical field, like the magnetic field. But if you treat the wave propagation, the electromagnetic wave, for example, the electromagnetic waves are propagating only due to the coupling between the electrical and magnetic subsystems. And if you treat some other phenomena, for example, these 2 new fast waves, you have to treat the coupling among all 4 fields, electrical, magnetic, gravitational, and torsional.
Can you also decouple or separate them?
Good questions. Zamsha is experienced in this in the experimental part. He works already for decades, and one of his problem of creating of such devices is to create a device in which the torsional field, the contribution from the torsional field is significantly more than the contribution from the other fields, for example, electrical and magnetic, but they still can't separate in their devices. Maybe it is possible to create other devices, but it is possible to measure the torsional field for example, for such object, cosmic object like our planet Earth. The torsional field is measured already for a long time for our planet Earth.
So it's not difficult. It's easy.
Can you see this?
Easier.
Oh, sorry. What was that, Rajan?
No, are torsional fields easier to create?
It is not good thing to use anti-gravitational. It is non-scientific.
Have you seen this before, Aleksey? Grabenikov's work. He uses like chitin. I'm not saying that this is true.
I don't know how to couple my research with it's some bugs, and yes, it is said that some bugs use all four fields to fly.
Oh.
Because it is not obvious why they fly, why they can fly, because it is not possible to fly for them, and they use first of all four fields, and this guy probably he died due to this his experiments because due to this radiation, and I don't know how to couple my research with changing of gravitation, but it is one of the way to cause change in the gravitational subsystem through via all three other subsystems. For example, it is popular to use magnetic subsystem. There are experiments when you have two generators of magnetic field and high magnetic fields, and when they separately in some directions generate magnetic fields, it results when these magnetic fields are interacting, it results in appearance of some gravitational fields. This means that there is a coupling between the gravitational subsystems and the magnetic subsystems, and therefore my theory there is a constant which response for this interaction. It is called the gravito-magnetic constant. It is an exchange constant. Yes, indeed, there is some exchange between each pair of subsystems, between gravitational and magnetic, between gravitational and electric, between torsional and magnetic, between torsional and electric. So you have to treat these four exchange constant between each pair.
Maybe we can use them as functors. Each one is like a functor, and something like a functional connects them.
Yeah, that would be interesting.
Yeah.
I used well-known theory, thermodynamics for piezoelectrics.
Piezoelectric.
Piezoelectrics, yes, they couple two subsystems: the electric subsystem and the elastic subsystems. Two field, electric field and elastic field. There are three elastic fields, and if you put instead of the electric field, magnetic field, you will have piezomagnetics. If you add magnetic field in your treatment to the electric and elastic field, you will deal with piezoelectromagnetics. And there are such materials. It is interesting that piezoelectromagnetics possess the magnetoelectric effect, which characterized by the electromagnetic constant. It is also an exchange constant, and this constant gives the speed which is several orders higher than the speed of light. This means that exchange between two subsystems, such as the electrical and magnetic subsystems, is several orders faster than the speed of light. This fact violates the theory of relativity by Einstein, and but it exists. These piezoelectric materials and the electromagnetic constant. This theory exists already for the last half century, and they exist in parallel worlds. This theory of piezomagnetics and the theory of relativity in parallel worlds, and
the superfluid. It's like superfluid, superluminar thing.
Superluminar.
Yeah.
Yes, I'm familiar with this word, superluminar.
We are working on that. Emmanuel we are going to work more on that next year.
My opinion is that superluminar, it's for some phenomena that can propagate slightly faster than the speed of light, only slightly faster. But you can see that these two new fast waves can propagate in a vacuum and in a solid with the speeds 13 orders faster than the speed of light. And there are some theory that treat graviphotons. They include two photons already, gravitational component, maybe torsional component. All four components they called graviphotons. There is such also direction. If you see, if you find in some article gravitophoton, you have to know then that they treat all four or only three subsystems, only gravitational and electrical and magnetic together, or gravitational, torsional, electrical and magnetic, all four.